Welcome, everyone, and thanks for joining us today. Today's discussion is focused on a simple idea that keeps popping up in modern data center design. As rack density increases, tolerances tighten. We're seeing higher heat flux, faster thermal dynamics, and more complex cooling architectures, often hybrid combinations of liquid and air. In that environment, control loops are less forgiving, as we're aware of, and small measurement errors can have a significant impact on performance, uptime, and energy use. In this session, we'll focus on real-world design and operational challenges, and what engineers, architects, and operators should be thinking about as densities continue to rise. Joining me today are two subject matter experts with deep field experience across data center cooling systems. One specializes in liquid side instrumentation and control, working closely with high density and liquid cooled environments. The other focuses on airflow, pressure, and containment performance, areas that remain critical even as liquid cooling expands. I'll ask each of them to briefly introduce themselves and their background. Chris, after you.
Thanks, Javier. My name is Chris Owens. I am a strategic account manager here with Setra, specifically focused on data center liquid cooling side on our industrial solutions business. Basically, anything from building and expanding our OEM account base, helping engineers and manufacturing teams design next generation data center equipment for liquid cooling specific applications.
Awesome. Thank you, Chris.
Hey, I'm Rajat. Thanks for having me. I'm the regional sales manager at Setra for the critical environment business. I'm based out of Dallas. And over the last 13 years, I've worked extensively with airflow management, differential pressure sensing, room pressure control, containment strategies, and critical environmental monitoring across mission critical facilities. My experience spans both traditional air cooled data centers as well as today's hybrid facilities where liquid cooling is being integrated with the existing infrastructure. So throughout this evolution, one constant has remained, and that is the operational visibility. The better we understand airflow, pressure relationships, and the environmental conditions in real time, the better we can operate these increasingly complex facilities with safely and effectively. I'm looking forward to this discussion by why cooling control and not just cooling capacity is becoming one of the biggest differentiators in modern high density data centers.
Awesome. Thank you both. So we'll start with our first topic, why higher density changes everything. So let's start at the foundation. For years, data centers were designed with relatively wide thermal margins. As rack density climbs, especially with AI and accelerated computing, that margin is shrinking fast. From your perspectives, what fundamentally changes in cooling behavior and control as density increases?
Well, I'll begin on this. For me, and what we're specifically on this side is the biggest changes in the system is systems are simply becoming less forgiving. Years ago, cooling systems had enough thermal margin that small measurement errors or flow variations often didn't matter too much. And today, that's just quite frankly not the case, because as rack densities climb and increase, we're concentrating much more heat into a smaller footprint. So liquid cooling, as what's become the talk of the town right now, is it responds very quickly and more efficiently, which is great from an efficiency standpoint. It also means that the system itself reacts much faster to any changes in flow, pressure, or temperature. So, for example, a sensor that's drifting away a little slightly, a pressure reading that's a little bit off, or a small flow imbalance can now create noticeably larger temperature swings than it would have a few years ago under different builds. So one thing that we're hearing from OEMs in particular is that they don't have time to catch the problems per se. The control system has to respond correctly the very first time because those operating margins are becoming much tighter. So it's very important that these are, this is a focus right away, and that teams and engineering squads can focus greatly on these issues proactively rather than having it just be a catch and fix circumstance.
Great. Thank you, Chris.
Right. So when people hear high density, They often think it's simply cooling challenge that liquid cooling will solve. But in reality, high density changes the operating behavior of the entire facility. So even in a partially liquid assisted environment or a fully liquid dominant environment, air never disappears from the equation. Air is still responsible for removing residual heat that isn't captured by the liquid loop. So it continues to cool power distribution equipments like UPS systems, switchgear, transformers, batteries, and network infrastructure. It also maintains environmental stability by ensuring temperature uniformity, humidity control, and particulate management throughout the white space. The difference is that higher rack densities, the operating margins become much smaller. So a few years ago, a small amount of bypass airflow or a minor containment leak might have had little operational impact. But today, the same small leakage can create localized hotspots and even uneven cooling distribution, higher fan energy, and reduced thermal efficiency. In other words, the system becomes less forgiving. So this is why containment effectiveness can no longer be assumed based on the design intent. It has to be continuously monitored and measured. And we need confidence that the cold air is actually reaching the equipment it was intended for, and that the hot air is staying isolated. Another important shift is the pressure relationship that becomes just as important as the temperature measurement, because temperature tells us what has already happened, whereas pressure tells us how the air is about to move. So understanding those airflow paths allows operators to identify the developing problems before the actual temperature drifts. So the conversation is no longer just about cooling capacity, it's about controlling airflow with much tighter precision or with much tighter tolerances. I think the key message that I would like to emphasize is air systems become less forgiving, not less important. So higher the density isn't just about adding liquid, it's about operating with faster dynamics and with smaller buffers across the entire thermal system.
That makes a lot of sense, and thank you both for the answer there. I think that brings us to control loops. As density increases, we often hear that control loops are less forgiving. What does that actually mean in practice for engineers and for operators?
Sure. Well, control loops are only as good as the information that they're receiving, right? So, for example, if your flow, pressure, or temperature measurements aren't accurate and repeatable, the controller has to compensate by becoming more conservative, right? Because why take those additional chances? You want to be more accurate with the sensing. So we often see, in particular, some of these systems where the pumps are running faster than necessary or temperature limits are set wider than they ideally like. And it's not because the hardware can't perform, it's because the operators don't have enough confidence in the measurement data itself. So, I guess in a nutshell, just to drive this home, the better your sensing accuracy, the more confidently these engineering teams and designers can confidently tighten those operating bands. And it means at the end of the day, more stable control, better efficiency, and less unnecessary energy consumption overall. And I guess one more time to drive it home, ultimately, accurate sensing gives engineers confidence to optimize the system instead of building large safety margins.
Got it. Thank you, Chris. How about you, Rajith?
Yeah, again, liquid cooling removes a significant portion of server heat, but it also changes how quickly the thermal environment responds. Because the heat loads are larger and more concentrated, there is much less buffer available for condition before conditions change. So that means the air side systems are no longer simply providing cooling; they're actively maintaining balance across the entire room, like fan speeds, containment pressure, C rack performance, underflow pressure, and rack airflow. All kind of become part of a tightly coupled control system. So one of the most important variables in this control strategy would be the differential pressure. So pressure differential is what ultimately drives airflow. And as most of us know, like all of us know, air always flows from higher pressure to lower pressure. So if you don't understand those pressure relationships accurately, we can't really understand where our cooling air is actually going. And poor differential pressure management can lead to several operational problems, like controls can increase the fan speed unnecessarily because they believe the airflow is insufficient, resulting in wasted energy. We can also kind of unintentionally collapse containment pressure relationships, allowing hot and cold air to mix. Or we can overcompensate in one area while starving the other, simply because the control system isn't actually seeing an accurate picture of the overall airflow. So as rack densities increase, differential pressure stops becoming being just another alarm point. It actually becomes an active control signal that continuously adjusts the airflow to maintain system stability. That's why a sensor accuracy and stability over time or long-term stability and faster response becomes increasingly important. Again, just to summarize this, you can't tune what you can't see clearly.
And I feel like that feeds into the point that tighter tolerances aren't theoretical. They directly affect how aggressively or conservatively systems must be operated. Would you agree?
Yeah, absolutely. Because as system density increases, we often hear that control loops are less forgiving. So, what does that actually mean in practice for engineers and operators? Am I kind of jumping ahead here, Zavi?
No, no. This is great conversation to be had.
Okay.
Um, I'll go into our next point. Our next topic in terms of sensing accuracy and being a differentiator. Historically, sensors were sometimes treated as basic instrumentation, something that just needed to be in the ballpark. At higher densities, why does sensing accuracy suddenly become a performance and uptime differentiator rather than a commodity?
Yeah, great question, Javier. I think one of the biggest shifts that we're seeing is that specifically with sensors, they're no longer just being used to monitor the system, they're becoming active inputs into how the system operates. So historically, many sensors were there to just answer simply fairly questions, is the pressure okay? Is temperature within limits? Is there enough flow? They're often viewed as instrumentation that would generate alarms if something went wrong, more on the reactive side, more rather than proactive. And today, especially in high density liquid cooled environments, the role has changed significantly. Those measurements are now feeding directly into the control strategy. Pump speeds, valve positions, cooling capacity, and even energy optimization decisions are all being driven by real time sensor data. Liquid cooling is incredibly efficient because water can remove heat much more effectively than air, but that efficiency only works if the control system has accurate picture of what's happening inside the cooling loop. The controller is only as good as the information it's receiving, basically. So example, if a flow sensor is reading low when the actual flow is fine, the controller may increase pump speed unnecessarily, and that consumes more energy, creates additional wear on the pumps, and it actually may mask the root cause of an issue. And on the other hand, if the flow is lower than expected, but the measurement is accurate enough to detect it, you could end up with an inadequate cooling at the rack or cold plate. And at today's power densities, which it's ever much growing as the days go on, you don't want you don't have much margin for those kinds of errors, right? And the same applies to pressure measurement. Differential pressure isn't just something that's operating the operator's trend anymore. It's becoming an important control variable that helps verify pump performance, identify restrictions, detect clogged filters, and confirm proper coolant distribution, and ensures the cooling loop is behaving the way it was designed. And I guess, just to tie it all up again and to reinforce the point, as AI workloads continue driving higher rack densities, I think measurement quality will only become more important, right? Because better sensing doesn't just improve reliability, it enables higher efficiency, better control, and ultimately helps operators get more performance out of the infrastructure they've already invested in.
Got it. Before going over to Rajith, I wanted to just make the point here that even he noted in his past answer about differential pressure being so necessary to understand with the airflow and circulation in that environment, and you noted here that it's also very critical in liquid cooling as well. So it is good to note that differential pressure across both sides of the system are critical to understand for engineers and operators. But Rajith, on to you.
Yeah, I think just to add to what Chris just mentioned, better visibility leads to better control, and better control leads to higher efficiency and greater resilience. So, in a traditional air cooled data center, operators generally had a fair amount of thermal inertia. So, if a control loop wasn't perfectly tuned, or if a fan reacted a little slower than ideal, they usually had enough room for a buffer to absorb those small deviations. So, as rack densities increase, those buffers become much smaller. So heat loads are more concentrated, temperatures can change more quickly, and even a small control error can have much larger consequences. So a response that might have been acceptable a few years ago may now result in localized hotspots, unnecessary fan energy, and unstable airflow. That's why when we say the control loops are less forgiving. So engineers and operators have less margin of error. So the quality of control inputs becomes much more important. And one of the most critical of those inputs is the differential pressure. So airflow doesn't move because of temperature; it moves because of pressure differences. So those pressure relationships determine whether cold air actually reaches the servers efficiently or they bypass the IT equipment entirely. So if the differential pressure measurements aren't accurate or stable, the control system is essentially making decisions with incomplete information. That can lead to fans running faster than necessary, containment pressure becoming unstable, and or hot and cold air mixing in ways that reduce cooling effectiveness. So as facilities become denser, differential pressure is no longer just another point in the building management system that monitors for alarms. It becomes an active control variable that continuously helps balance airflow, maintain containment integrity, and optimizes the fan performance. And as again, just kind of to summarize this, temperature again tells you what has already happened. Pressure is what tells you where the air is actually going.
Got it. Shows you that direction and that flow. It sounds like overall between your 2 points, in other words, better sensing doesn't just protect uptime, it also enables efficiency.
Absolutely.
Absolutely.
So, on to our next topic. Most facilities won't jump from air cooled to fully liquid overnight. What we're seeing instead is hybrid cooling, liquid where density demands it, and air everywhere else. Where do you see the biggest challenges when air and liquid systems coexist?
Yeah, and this is a very interesting question because we see all this movement, and it seems like the trend is pointing towards liquid cooling standardization. But it's really, it's false if you think that air-cooled systems are going away. And I mean, Rajesh would like to, rest assured there. But there's really a need for both, right? So most data centers are becoming hybrid environments. That's just a fact. Liquid cooling is becoming deployed where heat density demands it, and it's typically around AI and HPC workloads, while traditional air cooling continues supporting the rest of the white space, network, and power infrastructure, as well as the overall room environment within the data center. So the challenge is actually isn't choosing one technology over the other. It's getting both systems to work together as one coordinated thermal management strategy. So the liquid side naturally gets a lot of attention because that's where the highest heat loads are. But for the air side, it's still incredibly important, right? Even if you're removing most of the server heat with liquid, you still have the residual heat. You have power equipment, networking gear, and environmental conditions that need to be managed effectively and addressed. Where we're seeing challenges emerge is really at the interfaces between those systems. So, for example, if the liquid loop is removing more or less heat than expected, that directly changes the cooling load of the air system has to handle. And likewise, changes in room airflow or environmental conditions can influence how efficiently the liquid cooling environment performs. So they're much more connected than sometimes people realize. And from a sensing standpoint, that means operators need visibility into both domains, not just one. If the liquid cooling controls are working from one set of measurements, while the building management system on the air side controls are working from another, it's possible for one system to start compensating for the other without anyone immediately recognizing why. So we've seen situations where pumps are increased because temperatures appear to be rising, where the real issue is actually that the airflow imbalance there's airflow imbalance elsewhere in the room, or the opposite. Actually, the air system ramps up because it appears that additional cooling is needed when the liquid loop simply isn't being optimized correctly. So as hybrid cooling becomes more common, I think success will ultimately depend less on how good the individual air or liquid systems are and more on how well they're integrated with one another. And better sensing provides the shared visibility that allows those systems to coordinate instead of compete. And ultimately, hybrid cooling isn't a mechanical challenge, it's a controls and system integration challenges. It's done both on the actual OEM equipment as well as the facility level. And just the need for both air and liquid cooling systems and loops to work together and work as an integrated solution is essential for data centers and cooling moving forward.
Thank you, Chris. I appreciate the answer. Rajith, to you as well, where do you see the biggest challenges when air and liquid systems coexist?
I think with hybrid cooling, that's exactly where the industry is today, because most of the operators aren't entirely building liquid cooled data centers from scratch. They're actually retrofitting existing facilities or redeploying hybrid environment where some racks are liquid cooled while the others are air cooled. So on paper, that sounds pretty straightforward, but operationally, it's much more complex because one of the biggest misconceptions is that once liquid cooling is introduced, the air side becomes less important. In reality, the opposite happens. Air systems are simply expected to keep working, while thermal behavior of the room changes significantly. As more heat is removed directly from the rack, the amount of heat entering the room decreases, but it doesn't disappear entirely. So you still have the residual heat, network equipment, storage, UPS equipments, power distribution equipments, and all the supporting infrastructure still depends on effective air cooling. So what changes is the airflow itself. So pressure relationships that were established for a fully air-cooled room begins to shift. So airflow paths evolve. Some aisles require less cooling, while others continue to behave exactly as before. So if the air system continues operating using yesterday's assumptions, then it often becomes ineffective and unstable. That's why hybrid facilities require coordination and not separation. So liquid cooling system and air cooling system shouldn't be viewed as two independent cooling solutions. They're part of one thermal ecosystem. Let's say, a change in liquid cooling capacity affects airflow requirements. Likewise, changes in airflow can influence how effectively the remaining heat is removed from the room. So it's not no longer enough to monitor only, let's say, chill water temperatures or only the room temperatures. Operators needs to understand airflow patterns, pressure relationships, liquid temperatures, flow rates, environmental conditions, and equipment performance as one integrated picture. That's where modern sensing and controls become incredibly valuable. They connect those different pieces of information into a coordinated control strategy rather than isolated systems. Again, to summarize this, hybrid cooling fails when air and liquid are treated as two independent systems. And the most successful facilities manage them as one coordinated thermal system.
Got it. Got it. I think a point that you said there that I took away from it is that liquid cooling doesn't detract from air cooling, but still acts as a complement as both systems work together. And Chris, I noted in your response that you said hybrid cooling isn't just a mechanical challenge, it's a systems integration challenge. And that seems to be what we're seeing from this hybrid approach to having both systems there. So with that in mind, let's talk about energy and long-term operation. Cooling still represents a large share of data center energy use. How does better measurement help teams avoid the instinct to over-provision?
Yeah, so one thing that's constant is that we're seeing uncertainty that if there's teams that show levels of uncertainty, it always leads to conservative operations. So, for example, if engineers or operators aren't completely confident in the system and what the system is telling them, the natural response is to build extra margin within those systems. And it's understandable because uptime is the priority within a data center. And we've all heard about the millions of dollars that are lost due to seconds of downtime. But instead of operating where the system was designed to run, they'll often increase pump speeds, they maintain higher flow rates, widen the temperature limits, or leave additional cooling capacity online simply because they don't want to risk missing something. So the problem is that those safety margins come at a cost. Pumps consume more energy, cooling equipment works harder than necessary, and over time that can have a meaningful impact on operating efficiency. Better measurement changes the equation because it builds confidence overall. So when operators know that their flow, pressure, and temperature measurements are accurate and repeatable, they don't have to rely on large safety factors. They can go into it making smaller, more deliberate adjustments because they trust the data that they're seeing. If you know how your flow management, for example, is accurate, you can confidently reduce pump speed instead of leaving it at 100% just to be safe label. And if your pressure measurements consistently validate that coolant is being distributed properly, you don't have to compensate by over pumping the entire loop. So it's really just about replacing assumptions with the actual data in front of you. And we've been seeing this during commissioning and optimization phases. So instead of making broad adjustments and hoping performance improves, engineers can make targeted changes, immediately verifying the results and continue fine tuning the system in real time. And that creates a cycle of continuous improvement rather than simply locking into the system on the conservative settings for its entire lifespan. And as AI workloads continue pushing rack densities higher and higher, I think this is becoming even more important. Future efficiency won't come from continually oversizing cooling infrastructure. It will come from operating existing infrastructure much closer to its optimal design point, and that will require reliable, high-quality measurement data. And ultimately, accurate sensing gives operators something that's incredibly valuable to everybody. It gives them confidence. And when you have the confidence in your measurements and the data in front of you, you can operate with precision instead of relying on excess capacity. So I think the message to drill home here is just relying more on the data in front of you rather than just making assumptions based on what ifs. Trusting your data in front of you is always going to be key.
Regis, do you agree? Data-backed confidence?
100%. And I believe energy optimization is one of the biggest opportunities in our industry today. Because most data centers don't waste energy because the equipment is inefficient. They waste energy because operators don't have complete confidence in what they're seeing. So, when visibility is limited, the safest response is to operate conservatively. So, how do they do that? Is by running the fans faster, setting supply air temperature at a lower set point, having additional cooling units stay online just in case something goes wrong. And those decisions are understandable because reliability is always the highest priority. But conservative operation also means higher energy consumption and higher operating costs. So, better measurement changes that equation completely. When operators can have accurate, stable, and reliable information about airflow, differential pressure, containment performance, and environmental conditions, they can operate based on actual conditions rather than assumptions. And what that will result in is that allows the fan speeds to be reduced safely, supply air temperature set points to be increased without affecting the equipment reliability, and cooling capacity can be matched much more closely with the actual IT load. So just as importantly, small issues become visible much more easier. So instead of waiting for a server inlet temperature alarm to go off, operators can actually detect subtle pressure changes, deteriorating containment performance, clogged filters, or airflow imbalances long before they become operational problems. That shift kind of focuses from reactive maintenance to a proactive optimization. So, in my view, better sensing isn't simply about collecting more data. It's about giving operators the confidence to operate closer to systems' optimal efficiency without compromising resilience. And that's really what the future proofing means. Like as rack densities continue to increase and workloads become more dynamic, facilities won't succeed by continuously adding more cooling capacity. They'll succeed by making smarter decisions with cooling capacity they already have. So,
That makes
you know,
sense, right? To your
yeah, the
point about
facilities that
future
kind of
proofing.
yeah, the facilities that kind of invest in operational visibility today will be in a much better position to adapt to whatever cooling technology comes next.
Yeah, absolutely. I think you hit the nail on the head when you said future proofing. Better measurement isn't just about today's density, it's about staying adaptable as tomorrow's loads arrive. Ultimately, higher density doesn't just change cooling hardware, it raises the bar for measurement, control, and visibility across the entire thermal system. Thanks so much to our panelists for sharing their insights today, and thanks to everyone watching. We really hope this discussion helps frame how you approach cooling control as data centers continue to evolve. And for additional technical resources related to cooling control and measurement, visit our websites, gemsensors.com and Setra.com. Thanks. Bye.
Thank you.
Thank you.